Hello everyone. This lesson is about Prim's algorithm. So this is a method that we use in order to find the shortest path between vertices. Now in our first example, we're just looking at this network and we want to find the shortest path between D and H, and we have to include E. So the strategy for this one is to break the journey into two parts. First, I'll find the minimum distance between D and E. Then I'll find the minimum distance from E to H. So it's two sub-problems. Now for this one, we won't use Prim's algorithm because we're not covering the entire network. We're just doing a short little section of the network. So trial and error is appropriate. From D to E, common sense would say that we should either go along here, that's going to be 2 and 9 is a cost of $11, or here and here, that's only 7, that's better. Let's do that. Now, to get from E to H, we could backtrack by going back to C and then go along here, so 3 and 6 is 9. Or we could go down through G and then across, so 3 and 3 is 6, that's better. That's the one we will choose then. There is my shortest path. Now the dollar signs might represent bus fare to get between different stops. And this is a network of different bus stops. So if I want to go from D to H and I have to make a stop off at point E, there's my minimum path. We would write that down by going D, C, E, and then G and then H. If we had to give the cost, they didn't ask for it, but if we had to, we'd simply add those numbers up. So much for that one. Let's move on to the next one. We want to go from point B to point C, not including D. Now if we have to exclude a vertex, then cross out any of the edges directly connected to that vertex D. We're not to drive. If we were to go on those, we would end up going through D, wouldn't we? So now let's see if we can find, by trial and error, a minimum path from B to C. So the first guess, I'd come along here and then down to here. That's going to be 12. I wouldn't. Oh, maybe this is better. 4 and 4 gives me 8 to this point, which is less than 9, and then from here is only 11. That's better. Now I probably wouldn't go diverting further away, I'll end up adding more cost. So by trial and error, I think I have found the minimum, the shortest path, the minimum cost to go, and we would write this of course as B to A, E, and then C. Once again, we could add the costs if we wanted to. Now, if of course D had been allowed, that was excluded this time, but if of course D had been allowed, then a much shorter path would have been straight through here for a cost of only 6. But for some reason, D was forbidden in that particular scenario. Now let's move on from those ones which were just shortest path and it didn't cover every vertex. What if we wanted to cover every single vertex? In other words, we wanted a spanning tree rather than just a little subset of the vertices. There's this process called Prim's algorithm for finding the lowest cost spanning tree. We saw last time that a network can have many different spanning trees, but there's usually only one which is the lowest cost. So what do? We choose any vertex to start with. Well, if they all have to be included, that makes sense. It doesn't matter which one you start from. We look at the edges connected to that vertex and we choose the one with the lowest weight, the lowest number. We then look at edges connected to the little part of the tree that we've built so far and we add in the lowest weight one. We continue until we have the spanning tree. Now remember, a spanning tree must not have multiple edges, it must not have loops, and it must not have cycles. So as long as we avoid those features, we're okay. Here's an example. The water pipes between 6 regional towns need to be replaced. The graph on the right shows the distances between the towns. Now this is not where the pipes are, this is just the distances. We need to link each town. So we need a spanning tree to link every vertex, and we want a minimum spanning tree for this graph. So we'll apply Prim's algorithm. We literally pick any vertex to start with, it doesn't matter. Let's pick this one, just because it was there. Now what is the lowest weight or the lowest value edge connected there? We have a 9, we have a 10, and we have a 6. Well, the 6 is the minimum, so I'll add that one in. I now have a small tree involving vertex A and E, looking only at edges that connect directly to the highlighted part. I have a 10, I have a 7, I have a 10, and I have a 9. The 7 is the minimum. I will add this edge into my tree. Now looking at only edges. Now, this one, forbidden. That would form a cycle. We cannot have cycles in trees. So that 10 is off limits. It might even be worth crossing it out so I don't accidentally use it. Now I have a 9, I have a 14, I have a 7, I have an 8, and I have a 10. The 7 is the minimum. I'll add that one in. As the tree grows, there's going to be more possibles to consider. So now I have a 9, I have a 14, an 11, a 4, an 8, and a 10. The 4 is the lowest. Now I could not use the 8, that would make a cycle. I could not use the 10, that would make a cycle. So I can exclude some as I go so that I don't accidentally make something which isn't a tree. Now I only have to include vertex D, so I could use a 9, a 14 or an 11. The 9 is going to be the one. Is this thing a tree? Yes, because there are no loops, there are no cycles, and there are no multiple edges. Does it cover every single vertex? Yes, so it is a spanning tree. And because I applied Prim's algorithm, adding bit by bit and choosing the lowest value connection at each point, it is a minimum spanning tree. Now, in order to find the length of the water pipes, I simply add up the highlighted edges. So what have I got there? A 6 plus a 7 plus another 7 plus a 4 plus a 9. There's 1, 2, 3, 4, 5 edges. Yes. So 6 and 4 are 10. 2 7s are 14. That's 24 plus 9 is 33. And it said the distances were in kilometres, so I will need 33 kilometres worth of water pipe at a minimum to connect these towns. That's it for minimum spanning trees, and Prim's algorithm is the way we find minimum spanning trees. Thanks for watching.